The key here is that we want to design with geotechnical analysis. We don't want to find ourselves in a situation where we've designed something and then we have to prove that it works. What we want to know along the way is that the concepts that we're developing are appropriate and will solve the problems that we foresee happening. So, now that we have the data, engineering analyses must be completed based on the results of proper site investigations and testing. What we need to look at is, as Dr. Akayuli mentioned, seepage stability modeling. Do we need to consider earthquake loading? The answer is yes. More so in some areas of the world and less so in places like West Africa. Deposition and consolidation modeling of the tailings. As we're putting the tailings in, they go in a slurry format. In a slurry form. And over time they settle, they consolidate, they densify. So we need to know how much capacity we actually have. The tailings may go in at a density of, say, 1 ton per cube, and may consolidate to a density of maybe 1.5 tons per cube. So we need to make sure that we know how much space we need, how much space we have. Analysis should inform design, and not just confirm that it works. All facilities must be designed to a local standard at a minimum. We were just talking about how a lot of countries in the region are looking to Ghana as the leader of regulation, of guidelines, of standards, which is fantastic for us. There's plenty of countries that maybe their guidelines just say you need to consider stability. Right? So we need to use that as our minimum, but we might look at international standards, industry standards as appropriate to fill in some of the gaps. The Ghana regs in West Africa are regularly used, the Australian standards, the British standards, the Eurocode, Canadian Dam Association. Those are some of the standard internationals that we look at. So, when we're analyzing and designing, we want to do it in the same way that we would build something, from the bottom up. We talked about foundation investigation, then we talked about fill material. Same thing with our analyses. We should design from the bottom up. So, what's between us and what we want to protect? That's going to be our hydraulic barrier, our drainage systems. Do we need anything beyond a standard hydraulic barrier, a compacted soil liner? Do we need a geosynthetic? Do we need an underdrain system or a groundwater collection system? Regulations say that we do need to collect that underdrainage and that groundwater drainage. But do we need more? Do we need just a collection channel, or do we need a full blanket? It depends on what our goals are from an operations point of view and what our risks are from an environmental point of view. So we're going to talk a little bit about liner systems. Obviously, this has been interestingly debated discussion here in Ghana for a long time. And most recently, the discussion of compacted soil versus a geosynthetic material for hydraulic barrier. And before we're not going to debate which one is right, which one is wrong. We're just going to talk about the facts, just the facts. Okay? The number one fact that we need to consider here, guys, is that all liner systems have a finite permeability. Okay? HDPE geomembrane does have a permeability. It's actually referred to as a transmissivity, but it does pass water through it. Compacted soil does have a finite permeability. There is no such thing as an impermeable barrier. Okay? Concrete, water leaks through concrete. Steel, water will actually pass through steel on a long enough time. And we can look at those equivalencies. It turns out that a geomembrane, about a 60 mil geomembrane, a 1.5 millimeter thick HDPE geomembrane, has about the same flow capacity as a soil with a 10 to the minus 8 meters per second hydraulic conductivity placed in 300 millimeter lift. So 300 millimeters of soil is approximately equivalent to a 60 mil geomembrane. Okay? So there's actually a logic behind the regulations that look at some of these things, because we know that there are equivalencies between them.
So what are the key drivers for the liner decision? There might be a regulatory requirement, there might be an environmental requirement, it might be based on location. If we're somewhere that there is no low permeability material, maybe an HDPE geomembrane makes sense. If we're somewhere with very thick lacustrine or very thick lateritic profiles, maybe putting the geomembrane on top doesn't actually provide us much better performance than what's already in the ground. Okay? Maybe there's a geochemical issue. For instance, if we were to put something in that might geochemically interact with the clay, maybe that's a positive thing, but it might also be a negative thing. We might have something called sodium exchange, where we might actually increase the hydraulic conductivity of the clay. So it all depends. The same thing with the HDPE geomembranes, right? Or LLDPE, or even PVC if it's still being used. Some of those may perform poorly when you start looking at chemical interaction. It might actually start breaking down the plastic where it does not negatively impact a natural material. Okay? All liners have benefits, all liners have risks. When we talk about compacted soil liners, and I'm using compacted soil liner specifically because sometimes we talk about clay liners. Sometimes we want to have a clay liner. And in reality, very few places on Earth have pure clays available for use as clay liner. So if we start talking about, oh, we're going to use a clay liner's required here, clay liner's required there, what happens if we get into a situation where we don't have a pure clay? For instance, a clayey sand may provide us just as low permeability as that pure clay. Okay, so that's why we're calling it compacted soil liner. It may have a required permeability and required thickness based on regulations. The LI here says 10 to the minus 8 meters per second and a minimum of 300 millimeters compacted. Okay? It's the minimum that is required based on LI 2082. But it is dependent on material availability. If we can't quite achieve a 10 to the minus 8, could we put in a thicker liner? That's a discussion that we need to have with the regulators. Okay? You can show the equivalence again, and as long as the regulators agree and can understand the process and the mechanisms behind why we want to do something, then that gives us an opportunity for an alternative. But again, it requires the involvement and the engagement with the regulators so that we can make the right decision for the project as a team. There are some secondary benefits for compacted soil liners. Soil has a propensity to sorb different chemical constituents. It may actually lock up some of the chemical constituents that might leach out of a tailings mix. I'm not a geochemist. I know just enough geochemistry to get myself into a lot of trouble. Okay. So I will leave my my comments on that secondary benefit to, it is known that it exists. Every type of clay has different mineralogy, has different chemical composition, whether it's illite or a montmorillonite or a bentonite, right? And those have different chemical sorption rates to different constituents. So there are some secondary benefits to using compacted soil liner. There are some risks with using compacted soil liner, including non-homogeneity of aerosols. We need to have tight controls over those materials as they're going in, and good quality control on placement and on borrow. They're also subject to erosion in areas where we have high rainfall. We need to make sure that we've accommodated for the potential erosion of those materials, whether that's through continued maintenance of your compacted soil liner, whether that's through potentially protecting it with a fabric or protecting it with rock fill. Okay? So we just need to be thinking about those. Geosynthetic lining systems using a plastic, an HDPE, LLDPE. They come in all shapes and sizes and uses. We're starting to see more and more geosynthetics being used in Ghana for various reasons. We just need to make sure, again, that we're using the right products for the right reasons. Some of the benefits are
Availability of construction materials. If we don't have those low permeability soils, maybe we need to bring in a geosynthetic. What's the purpose of the lining system? Is it to separate internally, externally? Is it just the hydraulic barrier? What are the local regulatory requirements? Burkina Faso right now is actually requiring that all tailings facilities be lined with geomembranes. Okay? So they've taken a different tack and said, I'm not interested in the engineering, you must put in a geomembrane. So there are regulatory environments that require it. Geometry and facility and constructability. If we maybe have steep slopes where running compaction equipment is not practical, then geomembrane may be a suitable alternative. Suitability of geosynthetics relative to other design aspects. We talked about some chemical interaction potential. And is it a primary or secondary liner system required? Maybe a compacted soil liner is our primary liner, and we're using a geomembrane as a secondary liner. Okay? A belts and suspenders type approach. Standard geomembrane liner system is typically HDPE or LDPE or PVC, or there's as many resins as there are people who want to sell things out there. All of them have their benefits, all of them have their limitations, and we need to understand that, as well as thicknesses. You might see some plastics are very, very thin and some are very, very thick. Depending on what the material is going to be below it or above it, you might need a thicker or thinner geomembrane. Similarly, textured versus smooth. If anybody's ever tried to walk up and down a lined pond with a smooth geomembrane, they can be very slippery. So sometimes it's just a personnel safety issue. Maybe we want to use a textured geomembrane. And at the end of the, there's also additives. Anybody who's been through TARPA recently, TSF 5 has a white geomembrane. It has titanium dioxide. So the benefit of the white geomembrane is that it's less impacted by sun and UV. So it has a longer lifetime. It also doesn't expand and contract as much due to thermal effects. But it might be a little more expensive. There's things like scrim reinforced geomembranes that are being used for floating covers. So again, there's a lot of these products out there, and every product has a time and place. We just need to make sure that it's the right time and the right place for that product before we just jump onto it. Beyond pure geosynthetic products, we also have things like GCL, geosynthetic clay liner, which is a fabric with bentonite in between. And so that bentonite has very little hydraulic conductivity. The benefits to it are the hydraulic conductivity. The risks are, if you don't confine it very quickly, as soon as it hydrates, it becomes very, very weak. And once it becomes weak, there's nothing you can do to fix it. It just sloughs off and slides down. There's things like bituminous geomembrane, which is a fabric that actually has bitumen impregnated in it. Those are great in certain areas, although at very cold temperatures, they become very brittle and they actually crack and break, much like a pavement would. And in very hot conditions, they actually fall apart and start sliding around, again, much like a pavement. Then we get into some drainage and some more sophisticated geosynthetics like geomets and geosynthetics. Some considerations when you're using geosynthetics is compatibility with design. If we put a bunch of rock next to our geomembrane and then we put more rock on top of it, that rock will probably tear and shred that geomembrane, so it's probably not a good concept. Typically low shear strength with the interface, especially in GCL. Are we putting in an artificial shearing plane? Are we putting in a plane of weakness in our system inadvertently? We need to understand what impact that might have. We need to have proper development of subbase to prepare before we put down a geosynthetic. We might have differential settlement issues. Again, the nice thing with a thick layer of clay is if you do have some settlement, if you do have some deformation, the clay can actually accommodate it. It's not brittle. Okay? It doesn't tear. Where geotextile, geosynthetic is very, very thin, and if you do have that differential, it may strain enough that it actually tears. There's also things like cost implications. Geomembrane is going to be more expensive typically than soil if you have soil available. And long-term storage requirements.
the service life versus the containment requirements. The service life is one of the big topics around the use of HDPE and LLDPE geomembranes in the region. There's a feeling that if we bury this, that sooner or later it disintegrates, that it falls apart. And research does show that over a period of time you get into what's called thinning, service life thinning, where we start actually dissolving or decrepitating off some thickness of geomembrane. But that's really at the molecular level. It's not happening as quickly as we might think. This isn't a problem over 10 or 15 or even 50 years. This is kind of hundreds of years is where these things become problematic. There's been plenty of instances where landfills, for instance, have been exhumed that have had geomembranes below them, and they seem to be in reasonably good condition. We talked about shear strength being key in these. Anytime you put in a layer, we need to understand what that layer has on slope stability. So here's just some pictures of some geomembranes. This is a one-sided textured geomembrane where it's smoothed on one side, textured on the other. And here's how we glue them together using a welding machine. GCL, bituminous geomembrane, again, this is just an interaction. Here's our fabric with bentonite in between it. Now you can actually buy these that have fabric, bentonite, and a geomembrane, so you have a composite system in one. Geonets, geodrains. This is typically a fabric that sits over top of a woven, basically an interlaced plastic that can be used to pull water. And so these might be used in instances where we don't have drainage aggregate available to us, although they do have a tendency to crush under load, so you would want to put it at the bottom of, say, a big facility. Where these are really common is in leakage detection systems in very high required storage. So you'll see a compacted clay, then you might see fabric, and then you might see something like this below it, so that you have a way to understand, is there a leakage happening through our clay system. For instance, nuclear facilities will require secondary confinement and flushing. Again, with man-made materials, risks and opportunities are always present. And you have to look at quality, you have to look at where you're supplying these from. You have to look at every single roll. You have to do quality assurance during installation on every piece that goes down, as well as all of the welding. You need to have proper construction, CQA, and long-term performance compliance to understand. So once we've decided what type of hydraulic barrier we're going to install, we need to think about our drainage systems. Sometimes we need drainage systems below the liner to pull off the groundwater, because that groundwater is still non-contact. It hasn't come in contact with tailings. It's not contaminated. So maybe we want to put that back into the environment downstream so that we don't interrupt the groundwater system locally around the tailings facility. Maybe we want to capture that water and return it back to our tailings facility because our water balance says we're in deficit. Maybe we want to capture that water and monitor it to make sure that our liner system is working. Right? So all of those things have some benefits. The other thing is we might want to put a drainage system above our liner. It's called a tailings underdrain. And what happens there is any of the seepage water from the tailings that wants to go through the liner hopefully makes its way to our underdrain system. What that does is it pulls the water out, so it reduces our seepage across the liner, which is great for the environment. It also enhances consolidation. We can get a denser tailings because we're draining it from the bottom. And it also provides us a long-term closure opportunity. If we can't drain the bottom of these facilities, they just kind of stay wet forever. If we can drain the bottom of them, maybe we can get them dry enough that we do have a walk-away solution where we don't have an issue like what we saw at the very beginning. So here's kind of what these things look like. Here's kind of a typical groundwater drain, just a trench below your liner. Here's tailings under drain. Our liner is down below it. We have pipes and gravel that then get covered with erosion protection. This is kind of a standard detail for a type of under drain system. Some of us in the room might recognize this facility. What we have is headers, so we've got bigger pipes, bigger drains, and then we have secondaries that are smaller pipes, smaller drains. And that just collects the under drainage that's coming through. All of it cycles down, filters down to a collection sump where it's evacuated regularly. Now that we've figured out our basin, we've got a liner, we may or may not have various degrees of drainage. And then we need to talk about our embankment design. Our embankment design should be based on staged construction. The difference between a tailings facility and a water dam is that a water dam is usually built once. And then once it's built, it's operated. Water comes in, water comes out. And nothing ever really changes. A tailings dam, we don't need the whole thing at once. So we typically build it in stages. And what that does is it defers time, but it also defers construction costs. If I can spend $1 million tomorrow, I'd rather spend it tomorrow than today. So we need to look at our stage development throughout our life of mine. Do we want to build every year? Do we want to build every 2 years, every 5 years? Typically a starter facility, we might want to reduce our storage. We might only look at 1 year, because 1 year of capital deferment means a lot when you're trying to get a mine up and running. We're towards the end of the life of mine. 1 year might not be as important, so maybe we'll look at 2 or 3 years. Okay. Then we also want to look at the height and section that we'll be developing it to, and those decisions should be made throughout the process. In conceptual design, we should have an idea, and then when we refine that through our PFS and our detailed design, detailed engineering. Do we want our facility to be upstream raised, downstream raised, centerline raised, modified centerline raised? We'll show some photos and talk about those in a minute. Those decisions are going to be based on your material characteristics. They're going to be based on your climate. They're going to be based on your regulatory commitments. So for instance, here in Ghana, we classify our dams class A, B, or C. Class A and B must be raised using the downstream method, or otherwise agreed upon with the regulatory bodies. A Class C facility may look at centerline and may look at upstream raised dams, depending again with agreement from the regulatory agencies. So, analyses. What analyses do we need? We talked about this a little bit. We need seepage analyses to understand what type and quantity of water may be passing through our embankments. 1, so that we can size our secondary collection system, but 2, so we can understand the pore pressures in our dam. We can understand how the facility should behave. As our pore pressures go up, our risk goes up because our factors of safety come down. Right? Our stability reduces. And so we should run our seepage analyses to know what we expect, and then we should be able to modify those to know what happens if we don't get what we expect. What if our phreatic surface is higher? What if it's lower? What does that mean? And what that means is our slope stability. That's the next one. All right, we want to look at slope stability analyses, both because they're required, but then also what's appropriate based on our expected performance and loading conditions. There's a big discussion in the consulting industry right now to talk about what type of stability analysis is sufficient. Is 2D sufficient, or do we need to look at something in 3 dimensions? Historically, 2 dimensions has been sufficient. It's my opinion that it is still sufficient as long as it's done properly. And it's my opinion that it's conservative, because we're looking at just a plain passage. We don't get 3-dimensional effects, right? If you look at a stack of paper and you want to pull out a piece of paper in the middle of it, it's pretty easy to pull it out. Right? That's a 2D analysis. But what happens if I come on it, and if I come over and I push down on that stack of paper? Right now we have 3D effects. And now it's much harder to pull that piece of paper. There's also looks at what's called limit equilibrium, which is the current standard of practice for slope stability. Or do we need to go into numerical modeling, finite element modeling, finite difference modeling? Again, my opinion is that limit equilibrium is typically conservative, or should be done in a conservative way. And as long as we're properly accounting for material behavior, it should be sufficient. It's only when those methods start becoming close that we might want to look at something more sophisticated like 3D or like numerical modeling. If we have a required factor of safety of 1.5, let's say, and our limit equilibrium is estimating a factor of safety of 1.4, okay, we may want to look at something more sophisticated if the conditions require justify it. All right? Because we might get there. Or if our facility is at a factor of safety of say 1.7. So Class A facility in Ghana requires 1.7, which is one of the higher required factors of safety that I've come across internationally. If we're at 1.7 exactly, but we're not super comfortable with the site investigation work that we've done. Okay. Maybe we want to do some more sophisticated work. Maybe we want to do some more sophisticated analyses, but we only do more sophisticated analyses when we get more sophisticated material properties to justify it. We may look at settlement analysis. Because we're continually constructing these dams, settlement is less of an issue, right? Because if we lose maybe 10 centimeters, we're just going to add it back on when we do our next round of construction. We may want to use engineering analyses to look at pipe sizing for our drainage system, as well as material sizing and material specification for any internal drainage to the embankment. But oftentimes those are done based on experience and just functional construction sizing. Okay. One of the questions I always ask young engineers when they come and work for Knight Piesold, and one of my interview questions for experienced engineers is always, someone comes to you and says, we need to dig a half-meter wide trench for our drainage system. The question I ask is, what's wrong with a half-meter wide trench? Let's say that all of the analyses say a half-meter wide trench is okay. The problem with a half-meter wide trench is, how many pieces of equipment do you own that have a half-meter wide bucket? 0. Right? So sometimes when it comes to these drainage and these pipe spacings, we go based on the size of the equipment we're going to be using. Right? If I design something that has to be a half-meter wide, it can be a meter wide. It can be 1.1 standard bucket width. Right? So that's why we sometimes don't rely too much on analyses when we do some of those types of calculations. Similarly, in an embankment, we might show that our drainage might only need to be 1 meter thick. But placing 1 meter of material in thickness on an embankment is sometimes very challenging because of the slopes and because of the size of the equipment. So we might make some modifications. Okay, so here's a rough look at what we have for our slope stability analysis. Here's our model, here's our tailings, our embankment, our foundation. What we're seeing here is we've got our material properties. This is all very, very clear on my screen. I know it's not clear here, so I apologize for that. And here's our minimum factor of safety. Here's the results of our slope stability analysis. What this shows is that this embankment actually has a factor of safety of 1.3. So that's unacceptable. So what we did here is we varied our downstream slope from 1 and 2, 1 and 2.5, 1 and 3, 1 and 3.5. And based on our material properties, we see an increase in factor of safety. And we were able to go in and say, okay, we need a factor of safety of 1.5. That corresponds to, 1.5. That corresponds to a downstream slope of 1 and 2, or 1 and 2.5, whatever it is. Okay. So this is what I mean by designing with analysis. If we had just run off with our 1.1 and 2, we would have gone all the way down the road, we would have sent out our bill of quantities, we would have priced this thing, then somebody runs the analysis and says it doesn't work. So instead, I'd rather do something like this that informs our civil design, informs our quantities. So here's what these various facilities look like. Downstream raise, we've got our starter facility. Each of our raises goes sequentially downstream. The benefit here is we don't rely on the tailings for strength. We have continuity of our upstream face. If we were to use something like a geomembrane liner, it's very easy to install in that manner. We typically can use things like rock fill for our structural fill. The big issue that we have with these is what happens with the surface area here. It gets bigger every time, right? So that means the cost of each consecutive raise just goes up and up and up and up. Every stage you put on is more material is more cost, okay? This is what's called a centerline raise, where the center line of our dam just goes vertical. The benefit here is that, compared to this, is we reduce our fill volume somewhat, but now we start relying on the strength of the tailings. And so we need to make sure that we properly accounted for that strength. Then we have something called a modified centerline. What a modified centerline is it says, okay, we did go upstream a little bit, but the main centerline of our dam is built over the existing structure. So where we have our engineered zones, where we have our low permeability zones built above something that was controlled construction. We're not as reliant on the strength of our tailings. Actually, we shouldn't be reliant on the strength of our tailings at all if it's properly designed. Then we have something like this. Some people might call this modified centerline. Some people might call it upstream, where we just kind of march upstream with each raise. The benefit here is our costs go way down. The risk is that we're now much more reliant on the strength of our tailings, which is problematic. Or we have a true upstream raised dam, where we have our starter facility, we fill it with tailings, and then we step way in for another berm, and we step way in. These are very, very common in southern Africa, in places with relatively dry climate and low seismicity. There are a lot of places that don't allow these at all. And as an industry, it's a question that's going on. This is the type of facility that failed in the video I showed you at the beginning of the lecture. There are a lot, like I said, there's a lot of places that absolutely don't allow these, and don't even allow these. They might allow this, okay, and then they'll allow the others. So, as we talked about before, don't forget about the water. Embankment deformation becomes catastrophic when there's a pond, when there's water involved. And sometimes the water isn't just a pond. Sometimes the water is just the water that's in the tailings, the interstitial water that hasn't drained out yet. Okay? We talked about water balance today. We talked about dam break. During detailed design, those things need to be done and refined so that they're a functional item. Okay? A water balance especially is a living, breathing animal. It needs to be updated regularly. It needs to be reviewed regularly. And we should be using it to inform operations, not for accounting. Okay? Now, once we know it works, we can complete the design of the facility. It should include a detailed set of IFC drawings issued for construction drawings, a report detailing the engineering analyses used to support the design. This is huge. The engineering report. The drawings are all that we're worried about from a construction point of view. Okay? But a regulator, if you just come with a set of drawings, is going to say, well, these are absolutely beautiful drawings, but how do I know that it works? You've only told me what you want to do. You haven't shown me why we should be doing that. So that comes in with your detailed design report and your engineering analysis. We may do some support for permitting documentation from a geotech point of view, certainly from an environmental point of view we will. We should be working and thinking about operational guidance, operations maintenance manuals, operations maintenance surveillance manuals that help the owner and operator understand what did we think was going to happen? How did we expect you to operate the dam? Okay? If the design assumes that the tailings pond is far, far, far away from the embankment, that needs to go into the operations manual. Because if we don't have an operations manual, right, the operators might say, oh, this facility was designed with the pond against the dam. Those are two very, very different things, and the results can be catastrophic. The Mount Poly failure, for instance, in Canada, the reason it went from a deformation of an embankment to a catastrophic failure was that the operator had maintained the pond against the embankment. The facility was designed such that the pond was supposed to be maintained, I think, 300 or 500 meters away from the dam. Had the pond been that far away, we would have seen a deformation of the dam, but we wouldn't have had a release. And then we also need a detailed bill of quantity, the BOQ, for the construction plan. Then, now that we've connected all the pieces of the puzzle, we need to make sure the designs, the designers, the projects are all on the same page, okay? And by this I also mean we're not only building a dam, we have to operate it, okay? Have the designers of the pipe and pump system been on the same wavelength with the guys designing the tailings facility? If the pumps and pipes designers assume a 20-meter tall dam, and I want to build a 50-meter tall dam, they won't be able to get the tailings into the basin. Right? Once we have it all together, it's ready for permitting. And the big question is, have we included the necessary regulatory agencies along the way? Right? Or are we going to walk up to them and say, hey guys, here's our permitting packet, please give us a permit? We don't want to surprise the regulators, because the easiest thing for the regulators to say is no. And they don't need any justification for it. Right? And I think that's an okay thing. That's not a critique or a criticism of the regulatory agencies. If I come up to a regulator and I say, hey, we want to build a new tailings facility, you've got 12 months, I need my permit, please. And they don't know anything about the facility, they don't know anything about the design process, they don't know anything about the information that's available. What else can they say? It's unreasonable for us to expect them to approve that, right? But if we bring them in along the way, then hopefully when they get that document, the only thing they're doing is saying, finally we have it in writing. Once we confirm that the analyses are appropriate and we're compliant with all of our internal requirements, here's your permit, guys. We're happy to be a part of the team. Okay? Once we have the permits in hand, we can start construction. What about the water on site? Are we going to have to bring in water treatment, or are we going to be able to release the pond? Are we planning on maintaining a pond? If we've got acid-generating tailings, for instance, we might want to maintain a pond. There's nothing wrong with a wet closure. It just takes more planning and more thought than we do. And then does it fit in with our site-wide closure planning? For instance, if we have a certain amount of topsoil on site, are we planning on using all of our topsoil on the tailings facility, and then we have nothing left for our waste rock dumps, for our pits, for our roads? Or if, for instance, we have an old pit that we're going to be using, is there opportunities for maybe tailings backfill if it's designed and engineered properly? Is our final closure for that pit? What other options are out there? So the things to think about, what is the risk of limited design studies? As we limit ourselves, what are we actually limiting? And the answer to that is actually, we're limiting our opportunities in the future. Okay? Conservative designs are typically going to be more expensive, and they're typically going to be a lot more expensive. Okay. Did we take time to consider the other options? What options are out there? What did we think about? If we limit the time for the studies, we can limit our costs. Okay. One of my biggest frustrations as a consulting engineer, I'm sure Dr. Agayuli can agree with me, is when somebody comes and says, I need this done and I need it done in 2 weeks. Or I put in a schedule that says, this is going to be a 3-month-long study. They sign off on it, contracts are signed, kickoff study, and they say, oh, we really need to cut the budget, so we're only giving you 6 weeks to do the work. Right? For some reason, we think that the timelines and the costs that we generate, you're asking us for an opinion that, turns out those guys don't actually know what they're doing, but we still want them to design our dam. Right? So we need to make sure that we do the right amount of work. Okay? The feeling that I always try to portray is that the only way I'm ever going to be successful as a consulting engineer is if my client is successful as an owner and operator. Right? If I'm trying to squeeze a couple of dollars out of a client by dragging something on, then they're not going to be successful. And if they're not successful, who's the first person that gets cut loose? Me, right? If we propose small, we can always increase scope. This is something to be very careful about as an owner. I recently was just sitting in some meetings where I'm acting as basically engineers, specialists for the geotech studies that they're doing for closure program. And I went through the tender package with the client. They were looking at 5 or 6 different consultants. One consultant really seemed to have everything in their proposal. It seemed to be a bit of overkill for me. Right? I thought, it just seems like it's too much. Go back, see what they can think about, and if they can reduce their scope a little bit, because I don't think they need these 3 or 4 things right now. Let's get smarter before we spend that money. We had another consultant that came in and had kind of a bare bones proposal. They just wanted to do the very limited amount of studies. So we went through, the client came back to me and said, we just wanted your information, you to look at these for your information. We're going with the lowest bid, so you don't have to worry about these other guys and going back and asking them questions. We've made the decision. We're going with the lowest bid. So as we get into it, it turns out these guys bid low so they can win the work. And it's just change order after change order after change order. To the point now that the client has spent more money on the low bid contractor than they would have with the guys who actually thought through the process. Okay? So when we're going through our proposal phases for all of you budding consultants out there, and when we're going through the tender process from all of you budding owner-operators out there, don't think about these projects as complete black and white set in stone. Maybe you as the owner know a little something that can help out me as a consultant, give you what you need. Maybe I as a consultant have thought through something that either my competitors or maybe you yourself haven't thought about. Right? Because we all look at these things differently. So when we do have things like tender meetings and site visits for tender meetings, actually engage with those. Those shouldn't necessarily be someone standing here saying, this is the project that you will be bidding on, here's your minimum requirements, because I won't necessarily comply to those minimum requirements. I try to think of things as value add. Right? I want to give you your biggest value for your dollar spent. Other people might say, as long as I hit the minimum requirements, I know I'm going to change order these guys to death, I'm going to get my money out of them on the back end. Right? That's where it really helps to become a team and to work through these projects as a team. We want to have a good relationship. Right? A good relationship is worth its weight in dirt. But that dirt is really expensive. Right? I always tell my site representatives, you are there for oversight, not to be an overlord. You are there to help, you are there to guide, you are there to assist, you are there to think. You're not there to demand. And hopefully the client is in the same boat. Right? We're there to work through these problems together. We're working on a project that has a weekly meeting. That weekly meeting can get contentious. But at the end of the day, the end of that weekly meeting, the project is better off because we talk through the problems. Nobody goes in and says, my way or the highway. They go in and say, guys, we have a problem. And somebody might say, here's the solution. And somebody else might say, that can't be the solution for these reasons. Here's the solution. Someone else says, that can't be the solution because of these reasons. We work through it as a team to sort out the problems, to find the best solution. one thing here I'll throw out as well is that earthworks is not the same as TSF construction. Recently, we've seen a lot of new contractors bidding on a lot of work. Some of them have done fantastic work. Some of them have been some of the best contractors that I've worked with. Some of them were guys that were really, really good at mining, and so they have a lot of equipment, but their job stopped. So now they've decided to become a contractor, and digging a hole is not the same as building a dam. And similarly, building a dam is not the same thing as digging a hole. Those are specialist services, and we need to understand the difference between the two and how they work. Bulk earthworks is not the same thing as layered detailed works. Okay. Construction planning, cost estimating, and constructability reviews can be very beneficial. I don't want to design something that can't be built. Right? We actually are starting to develop a team within our company that focuses on construction and constructability. So the benefit there to a client, for instance, would be we can sit with a guy like Billy Archer and we can talk through the constructability. We can talk through some of the problems. We can take that back and we can offer that service now to all of our other clients. And we can say, I know what's wrong with your half-meter wide trench now. You can't build it. Or now I know what's wrong with this design because it's too steep or the valley doesn't make sense to them. So we can put that into our analysis, or we can go to a guy like Billy Archer and say, Billy, I need you to look at something. Does it make sense to build this in this progression? And he'll come back and he'll say, you want to do ABC, but really you need to do ACB. And it'll make your life way easier. Okay? Everyone is aiming to please when it comes to construction. All right? Everybody wants to be the guy that saves the money. Everybody wants to be the guy that has the genius idea, and that's great. But we need to be careful of false optimism and compounding optimism. If I'm trying to save you 10%, and you promise to save that guy 10%, and he's promised to save that guy 10%, and then finally gets to the GM who's expecting 50% savings, all of that really drives our costs on paper down and makes our budgets kind of useless. So there's two comics that I like when it comes to construction. I don't know if Dilbert, is this, it's probably not a comic here. So this guy's name is Dilbert, and he's the typical computer engineer. Very smart guy, very brainy kind of guy. So he's working, and someone comes up and says, I need a budget estimate for my project, but I don't have a scope or a design for it yet. So how much is it going to cost to build my dam? But we don't know what it's going to look like yet. His estimate, $3,583,729. Her response is, but you don't know anything about my project. His comment is, neither do you. Right? There is no cost for a tailings dam. There's only cost for a specific project. Okay? And the other one is, I didn't have any accurate numbers, so I just made one up. I was writing a number up on the board, $4 million. Studies have shown that accurate numbers aren't any more useful than the ones you make up. Somebody challenges it. How many studies said that? 87. Okay? Our numbers mean something, and we need to have numbers that mean something. But we find ourselves in these situations all the time. Right? Somebody comes and says, how much for my site investigation? Well, where's your site? Where's your site investigation? What's going to be built there? How much for my tailings dam? There's some rules of thumb out there. About $1 a ton is a reasonable rule of thumb. But it shouldn't go into a cost estimate. It shouldn't go into an AFE. It shouldn't go into budgetary numbers for a big company. Right? Okay, so we talked about oversight, not overboard. The important thing is we get it done efficiently, we get it done correctly, and we get it done safely. Beware of external pressures during construction jobs. Everybody's going to want different things. And the important thing is we get it done efficiently, we get it done successfully, safely, and we get it done correctly. Right? Because if we don't, 252 known people died in the job. 100 plus still missing. That's the cost if we don't get it done right. I'm not saying those guys didn't construct it correctly, but I'm saying dams can fail because they weren't constructed correctly. And dams have failed because they weren't constructed correctly.